Okay, good morning, everyone. Am I audible?
Yes, sir.
Okay, so let's start. So we have discussed in our last classes, this is the control actions, okay? And last class, we have to classify the different types of control actions. That means the proportional controller, that is derivative controller, integral controller, and also proportional integral and derivative controller. And we have to discuss in details in previously proportional controller and derivative controller some parts also. Okay, so we will continue the another part also. And your syllabus, that is the internal exams, I am telling the previous classes also, and also remind that the module 1 and module 2, that is module 1, we have to discuss the introduction to principle of control system. There are lots of terms and topics we have to cover. Please go through the class notes in the Google Classroom portal, and also you have to see in the previous video, that is the YouTube channel video. Okay, so there are module 1, introduction to principle of control system, and also module 2, that is the time domain analysis and frequency domain analysis. These are the basically your midterm 1 exam syllabus. Okay, is it okay? Is it okay, all of you?
Yes, sir.
Okay, so first we have to discuss, that is derivative controller in the next part. My whiteboard is visible, everyone?
Yes, sir.
Okay, so derivative control. So just first I am drawing these pictures, then the given the idea. This is the first input, first summing point we have to given here. Then another blocks. Then processor plant. This is the, here we have to use the second order system. Then finally we have to calculate it from here, the output that represents CS. This is the RS plus, and also here we have to attach one unity feedback systems throughout the output to the first summing point also. This is error of the system, that is ES. We know that first, that is the first blocks, this is a controller part, 1 plus S into TD. Another one, the signal is coming from the controller through the error of the system, that is EAS. And this is a second order systems, omega n square by S into S plus 2 zeta omega n. Okay, so this is the basically block diagram of the derivative control. Of derivative control. So in this derivative control, we have to calculate the actuating signal consisting of proportional error signal, which is added with the error or derivative of the error signals. Okay, so these derivative control signals, so this action the actuating signal consist of proportional error signal added with derivative of the error signal. Okay, so these derivative control actions, basically the actuating signal, it consists of the proportional of the error signal which is added with this system. This is the basically error signal we have to calculate from the input to the controller part. This is expressed, that is a ES. So this error signal which is added with the derivative of the error signals. Okay, so therefore the actuating signal for the derivative control action is given by what is the equation? This is the EAT, that is a time respect. It is equals to error of the system, that is ET, plus TD into derivative of the changes, that is a DET dt also with respect to the time. So this is the basically actuating signal for the derivative control actions. It is given by, that is EAT, this is equals to ET plus TD into DET dt. Okay, so here TD is the basically time constant. So this is the number one equations. Sorry. So here TD is the time constant. Okay. TD is the constant of the time. Okay, up to this part it is clear, all of you. This is simple expression of the derivative controller part. Is it okay, all of you? Is it clear, all of you? No one is confirm me.
Yes, sir.
Okay, so after that we have to apply the Laplace transform of these equations. Okay, so we go the next page. So now the Laplace transform of the actuating signal incorporating derivative control. Derivative control is, so we have to apply the previous equation, the Laplace transform. Okay, Laplace transformation. So the equation is, that is EAS, this is equals to also ES plus S into TD into ES. So this is the basically the Laplace transformation of the derivative equations of the previous one. Okay, so For this second order unity feedback control system, this is the basically represent the derivative control actions. Okay, so this is the basically the derivative equation, that is the EAT. This is equals to ET plus TD into DET dt. This is the time dt. TD is the time constant. When we have to apply the Laplace transformation this equation, the equation is coming, that is EAS equal to ES plus S into TD dot ES. Okay, so this is the basically equations of the derivative equation, derivative controller part. So now when you have to apply, when you have to calculate the transformation function of the given equation, given figure in the previous one, so from the block diagram, which block diagram I am drawing in the first slide? So this is the block diagram. We have to calculate the transfer function. This is the TF. It is equals to, we know that this is CS by RS. Okay. So what is the equation of this CS by RS? That is 1 plus S into TD, S into TD into, this is the second order system, we know that, that is the equation, that is omega n square by S into S plus 2, sorry, S into S plus 2 into zeta into omega n. This is also, and what is the RS? That is 1 plus into 1 plus S into TD dot, this is omega n square by S into S plus 2 zeta omega n. Okay, so this is the basically transfer function. So we have to written this equation, that is CS. We simplified these equations. The equation is coming, that is CS by RS. This is equals to 1 plus S TD into omega n square divided by S square plus 2 zeta omega n plus omega n square TD within bracket close into S plus omega n square. So this is the basically required transfer functions of this given equations. Okay, so this is the basically derivative controller. There is a block diagram. This is a second order system, we know that. So this is the omega n square by S into S plus 2 zeta omega ns. So when you have to calculate the transfer function, that is the CS by RS, that means the ratio between the output of the system to the input of the system, that means CS by RS. So we have to return this, this is the basis value. Then you have to simplify this equation, because this one and this one is cutting down and you have to calculate it. The equation is coming 1 plus STD into omega n square divided by S square plus 2 zeta omega n plus omega n square TDS into, sorry, plus omega n square. Okay, is it okay, all of you? So this is the basically characteristic equations of the derivative controller part. So now the characteristics equations equations for the overall transfer function is, so you have to given the equation number also. This is basically number 2, another one, this is number 1. Okay, so transfer functions is, this is the characteristic equation, that is a square plus 2 into zeta omega n plus omega n square TD into S plus omega n square. This is equals to the 0. This is the third number equations. Okay, now we have to calculate from here, that is the damping factor, that is zeta. So as per equation 3, the damping ratio of the system using derivative control So we have to return, that is zeta dash, this is equals to 2 into zeta omega n plus omega n square TD divided by 2 into omega n. Okay. So this is the basically required damping ratio of the derivative control systems. Okay. Up to this part, it is clear, all of you? And we have to simplify this equation, that is zeta dash, this is equals to zeta plus omega n dot TD divided by, that is 2. You have to simplify this equation, that means this one by this one plus omega n square TD by 2. The simplified equation is coming, that is zeta plus omega n TD, this is zeta by 2. Okay. Is it clear, all of you?
Yes, sir.
Another part, what is the steady state error, this derivative controller part. So the steady state error for the unit ramp input function is, that is equals to, we know that is ESS, that is the error of the system, that is limit S tends to 0 S into ES. We know that this expression. So this is ESS, this is equals to limit S tends to 0 S into, what is the value of ES? Because we know that it is a ramp input function, that is 1 by S square dot. This is the basically required function, S into S plus 2 zeta omega n divided by A square plus 2 zeta omega n plus omega n square TD bracket close into S plus omega n square. Okay. So now you have to put at the value, that is limit S tends to 0. So the value is coming, that is ES, this is equals to 2 into zeta by omega n. So this is the, because damping ratio of error of the, thank you, error of the system of the derivative controller part. Okay, so this expression, it is very important. So one little bit this question is coming in your semester paper in the proportional controller, either proportional or derivative or integral or PID controller part. So it is clear, all of you? Is it clear? There are 25 members, that is a student, both department, but response it is not given. Sometimes is one or two is responses and others, that is the class is going on, but they are not answering me, they are not responses me. Is it clear?
Yes,
Yes,
sir.
sir.
Okay. So next part we have to go, that is the integral controller part. Okay. Integral control or controller part. This is expressed, that is the I, capital I. And derivative controller, you know that is the D. We know that D. And P is the, that is the proportional controller. P is the proportional controller or control. So P for proportional controller, D for derivative controller, and another one is the I for integral controller. And the last summation part, that is a P plus I plus D, that is a proportional plus integral plus derivative controller. So first, I am drawing the pictures of the block diagram of the system. This is the first input RS, first coming in the first summing point. This is the first blocks, that is one controller part, 1 plus Ki by S. This is the basically integral controller part. And then this is the basically process or plant. There is a second order systems here we have to use this, and then finally output from here. That is omega n square by S into S plus 2 zeta omega n. Okay, and this is the output CS. And unity feedback we have to attach in this system to the output to the first summing point. Minus, this is plus, this is the ES. Okay, and this is the error of the system output to the apply to the processor plant EAS. This is a block diagram of integral control. Okay, so this integral control action, basically it is actuating the signal consisting of proportional error signal, which is added with the integral of the error signals. Okay. So for integral control, action, the actuating signal it is consist of proportional error signal added with integral of the error signal. So therefore, the actuating signal for integral control action is given by what is the equation of this integral controller? This is EAT. This is equals to ET plus KT integration ET dt. Okay, so this is the basically the integral control actions, the actuating signal which is consist of the proportional error signals which is added with the integral part. Okay, so this is the basically error of the system. This error signal it is added to the one controller part which is the integral controller part. Okay, this integral controller part of the error signal. So what is the signals it is coming from this integral controller part? This is the EAT. This is equals to ET plus KT into integration ET dt also. Okay, so here that is a KT, that is KT. This is the basically constant terms. Okay, so when you have to integrate these equations, so here, so this is Ki, not this is KT. Okay, this KT means that is the integral constant, that is Ki. The Ki is a constant which is integral constant also. Okay, next you have to apply the Laplace transform in this equation. So this is the basically equation 1. Now we have to apply the Laplace transform in the equation 1. So the Laplace transform of the actuating signal incorporating integral control is, that is when you have to apply the Laplace transform of the given function, that is equation is coming EAS, this is equals to ES plus Ki, that is the integral constant, into ES by S. This is the required equation number 2. Okay, so when you have to apply the Laplace transform of the given equation, that is the EAT, this is equal to ET plus Ki integration of ET dt. Okay, so the equation is coming, this is the EAS, that is equals to ES plus Ki ES by S. Okay, up to this part it is clear?
Yes, sir.
Now we have to calculate the transformation functions, that is the TF. So from the block diagram, the transfer functions we have to calculate, that is equals to, we know that output of the system, that is CS, to the input of the system, that is RS. This is equals to, we have to written here, first part 1 plus Ki by S, and we know that this is a basically second order system, that means omega n square by S into S plus 2 zeta omega n, and RS we know that 1 plus Ki by S into omega n square by S into S plus 2 zeta omega n bracket close. And here we know that feedback is also unity feedback. So you can go through the pictures, that is a block diagram. So here you can see this is the one feedback loops we have to attach, but here no block or no value is given. So that means this is the basically unity feedback system. So what is the value of unity feedback? We know that that is a 1. So that's why we have to multiply it 1. That means GS, this is the basically GS by 1 plus GS into HS. HS is the feedback. Is it clear, all of you? Now we have to simplify this equation, that is CS by RS. This is equals to, when you have to calculate the, I am written the final equations, that is S plus Ki into omega n square divided by, that is x cube, that plus 2 into zeta omega n square plus omega n square S plus Ki, that is the integral controller constant part, into omega n square S. So this is a equation number 3rd. Okay. So now the characteristics equations, for the overall transfer function, is, so this is a basically 3rd order system, that is a cube is coming, that means the 3rd order system, 1st order, 2nd order and 3rd order, that is S cube plus 2 into zeta omega n square plus omega n square S plus Ki omega n square. This is equals to 0. This is the number 4 equations. So in this integral controller part, we have to calculate the 3rd order system. So in your syllabus, in this frequency response analysis, in this syllabus we have to calculate it up to the 2nd order system, but in the later module, that is a module 3 and module 4, we have to calculate the 3rd order system in the different method we have to use, that is a Routh-Hertz criteria method. Okay. So when we have to go the module 3, we have to calculate the 3rd order system using the method of Routh-Hertz criteria. Okay. So that part we have to calculate the elaborately. Now we have to imagine that this is basically 3rd order system. So the transfer function of the in the block diagram, representation the forward path transfer function is GS, it is equals to S plus Ki, that is the integral controller part, into omega n square by a square into S plus 2 zeta omega n. We know that this is the required number, class equation 5, I think. Okay. Okay, everyone write your own name and roll number in the chat box also. Okay. And Gautam is present. Are you hearing me, Gautam? Gautam is present. Gautam is not present. Sandeep? Are you hearing me, Sandeep?
Yes, sir.
Okay, you take a screenshot, okay, for the attendance purpose in single page, and after the class you have to send me.
Okay, sir.
Okay, so we conclude the classes, that is the transfer functions. So now when the feedback path, that is the, we know that here feedback, that is a unity feedback, that means the feedback path transfer function is, we know that the value of feedback factor, that is HS equals to 1. So the transfer function relating error of the system, that is ES, and RS, that is the input of the system, is given by, that is ES by RS. This is equals to 1 by 1 plus GS into HS. We know that these equations. So easily you have to calculate it from here. And what is the basically error, the steady state error response analysis? Steady state error value of the integral constant pad, that is ESS equals to 2 into zeta by omega n. Okay, so you have to apply these equations step by step, and you have to calculate the value of the error of the system. So finally we have to calculate it. This is the ES, this is equals to RS into, that is a S square S plus 2 zeta omega n by S cube plus 2 zeta omega n square plus omega n square S plus Ki, sorry, this is omega n, okay, Ki into omega n square. So we know that this is the parabolic input we have to apply it in the third order systems, that is a 1 by S to the power cube. So the value, it is